Good afternoon, everyone. So today is the eighth interaction session on reliability-based structural design. So this course is instructed by Professor Arunashis Chakraborty, IIT Guwahati. So my name is Devashish Panda. I am a research scholar and Prime Minister Research Fellow at IIT Guwahati. So I have been allotted to this course as Prime Minister Research Fellow TA, PMRF TA. So every Sunday, 3 to 5 p.m. we meet and discuss the current week concepts, solve assignments, uh, via pen and paper, and also solve different kind of problems using MATLAB. So today we will go through the simulation based reliability analysis. So during last few weeks we went through the gradient based reliability analysis, where we have solved different problem using first order reliability method, as well as we have solved different problem using second order reliability method. Basically we have solved different problem using the gradient based form. So today we will see the simulation based reliability analysis, where first we will go through the Monte Carlo simulation, that famous Monte Carlo simulation. So we will go through the concept first, then we will code it, and we will solve different kind of problems, and we will verify the results we are getting from the Monte Carlo simulation with the gradient based reliability results, like form and SOM results. Already we have these results, then we will move towards importance sampling and adaptive sampling method. That means today we will go through the simulation based reliability analysis. We will code it, we will solve different kind of problems, and also the problems that can be solved using pen and paper, which will be beneficial for your assignment purposes. So let's quickly start. So actually today I am suffering from that eye infection. So today we will wrap up the session as soon as possible. So let's start. Like, before going to the simulation based technique, let's quickly revisit the gradient based reliability analysis. Like, during the last few weeks, we have solved form first order reliability method. So recall, in first order reliability method, what we actually did, like we linearize the limit state function using the first order approximation of the Taylor series of the limit state function around the mean. And for the second order reliability method, we approximate the function up to, or we truncate the series up to second order. That means in form we considered the first order approximation, and in SOM we considered the second order approximation. And what we have seen, that first we have a limit state, we need to convert it into Z space, that means standard normal space. So we need to convert it into GZ. Now what we need to find out, we need to find out the distance of the limit state from the origin in standard normal space, and that actually was the definition of the Haushofer-Lane reliability index. So we have solved using Haushofer-Lane reliability index. So how we proceed, we already have solved. Like, we start with some initial beta and initial direction cosines, then we will continue the iteration until the convergence will achieve. Like for this example, we have already solved this cantilever beam problem, where in the limit state we have two random variables fy and z, and after solving this, we have seen that after third iteration we will get the beta value as 2.2577, and corresponding pf we have calculated this. And further we can improve this result by incorporating the second order reliability method. Already we have seen the Brightung approximation and weight approximations, where the uh, curvature, or the information about the curvature, will incorporate to the form result, and the form result will get eventually accurate. So now the question is, to solve this, we need to have a limit state, we need to convert it into standard normal space, then we need to look for the minimum distances or minimum values. Now the question is there any method by which we can actually verify the result of first order and second order reliability method, or by any way we can solve the reliability? And the question is, yes, we have the simulation based techniques, which is actually quite handy, but eventually actually needs more computational effort. We will check. Okay, so, like, if I want to give you a quick overview of the Monte Carlo simulation or the simulation based technique. So let's quickly see its overview. The concept is very simple. Like, what do we need to do in simulation based technique? First, we have a limit state. In the limit state, we have the random variables. So what we need to do? We need to generate random numbers of these random variables. So here you can see we have two random variables, f, y, and z. This is your limit state function, and we have generated random samples of fy and z. Okay, we have the random samples. Now I will come to it, that how we can generate the random samples. For now that we have generated random samples of these random variables. Now with that random sample, what do? We check our gx, how many times the gx is greater than equals to 0. That means we have, for every set we will have one fy and one z. So put these values in the limit state function and check how many times the limit state function is greater than 0 and how many times the limit state function is less than equals to 0. Now for the failure, so recall, for a limit state, if it is less than equals to 0, we consider this as a failure. So for the failure, we assign one indicator function that will tell that when the gx will fail, it will take the value 1 and store the value. So now we have the values, how many times the limit state become less than or equals to 0. That values by the indicator function we will have 1, store the values. Now using the classical definition of probability, what the classical definition of probability says, like if we have an event A occurs n times out of n trials, then the probability of getting A is nothing but the na by n. Like that, or likewise, we can calculate the probability of failure. Probability of failure is nothing but the summation of the failures. Already we have, identified this using that identifier I, which when the gx will be 0, that will take the value as 1, right? Now total summation of this failures divided by n, total number of failures, will give us the probability of failure. It's quite handy. It will work on the basic definition of the probability, classical definition of the probability, and we can get the probability of failure. Now here two big question is there, like how we can generate the random samples, and this n, how many samples we need to converge our result. These two are the big questions. So we will go into that later. So first see, or first try to get this concept more clearly. Like what I said, first we will have a limit state function. We need to generate random numbers or random samples of these random variables. Then we need to check how many times with this random samples the gx is greater than 0, and greater than 0 we know it's success. So we are here estimating the failure probability. So basically we need to count the failures. So for the failures, we assign one indicator function which will tell that when the gx will less than equals to 0, that will store 1. That means if we sum all these indicator functions, when this limit state get 0 or less than 0 divided by total number of samples, we will get the probability of failure. Like if we quickly solve one small example, then we will go into it deeper. So let's say we have this. It's a very simple question, like just to get the clear concept of this mcs. Like here we have a gx is equals to x1 x2 minus 750. Okay, and this question says we have sampled some points like 1, 2, 3, 4, 5, and 6 samples we already have, like random samples we have. So if we have this much of samples, and if this is my limit state, so what should be the probability of failure? So what I said, so based on the samples, we need to check how many times your gx is getting 0 or less than 0. So check for the sample this x1 and x2, put the value of x1 and x2, this is greater than 0. That means for the safe domain, we don't assign any indicator value. Similarly, we will check for the rest. Like here we can see that for 36 and 20 we will get one sample where the gx become 0. So we have one indicator function and second. So we have two failures out of these 6 samples, or we can say that we can have two times the gx will become 0. That means total number of failures is 2, total number of sample is 6, and probability of failure is nothing but summation of these failures, that means 2 divided by 6, that means 0.33. So the concept is very clear, but the problem is how we can generate the random numbers first thing, and how should be, or this n, how we can get this number of simulation, or what should be the exact number of simulations to get the desired probability of failure. So we will investigate these two things and we will code it and check using MATLAB also. So let's go to our topic. Now I think this concept has clear, like how this Monte Carlo simulation work, or the simulation based technique actually work. So let's quickly answer the first question, how we can generate the random numbers, how we can generate the random numbers. So for this different kind of you know random number generators are available. Now in MATLAB we have the privilege of using the MATLAB. So we in MATLAB there are inbuilt function to generate different uncorrelated independent random numbers depending on their properties. So first thing, we need to uncorrelate the random variables. Recall in our gx, say for example, say our gx is x1 x2 minus some value, say 1140. Now this x1 x2 can be correlated. We have seen that the case when we have solved the first order reliability method. So first what we need to do, we need to uncorrelate it. So we need to perform one orthogonal transformation, and we have already seen that x is nothing but v into y. Now what will be the properties of y? E of y, that means uncorrelated space, the expectation will be v transpose e of x, and v is nothing but the eigenvalues of the symmetrics, and the uncorrelated covariance matrix also we can see like v transpose cx into v, and that is nothing but the eigenvalues of this cx matrix. So we need to perform the eigen operation first to uncorrelate the correlated random variables. Now once we have the uncorrelated random variables, what do we need to do? Now we have the privilege to use the MATLAB function. Like here in this step, we have uncorrelated the correlated space or correlated random variables. Now let's see how we can get the random variables. Now here, this is the MATLAB inbuilt function. I have directly copied it, and actually we will code it. That's why from that function file I have copied it, and we will see how we will code it later. Like for the normal random variable, we can generate like random function is there. For random normal variable, we can directly put the normal variable here using mu and sigma. Then the MATLAB will generate the random normal variables using this mu and sigma. Likewise, we can generate uniform, log normal, Rayleigh, and gamma, all the independent random variables using the inbuilt MATLAB function. Okay, so by this way we can get the random samples. Now once we have the random samples, now our task is easy to solve the uh, you know uh, MCS, Monte Carlo simulation. Okay, so Bob, actually we already have started that Monte Carlo simulation thing. So for you, I just quickly recap this thing once. So are you there?
That, yes, I'm there. Thank you very much.
Okay, so already we have seen that the gradient based reliability analysis like form and song we have seen. Now the question is there any kind of another way to solve the reliability problem? Yes, we have like simulation based technique. Now in simulation based technique, what we generally do, now focus on that. Like we, if we have a limit state, this is our limit state. In limit state we have two random variables fy and z, right? So in simulation based technique, what we do, we generate the random samples of this random variable. So here look, we have generated the random samples of this fy, this is z, and this is fy. Okay, now using that random samples, we put it in our limit state function and check how many times this limit state function is greater than 0. And the gx is greater than 0, we call success, and gs is less than equals to 0, we call it failure. Now we are calculating the probability of failure. So for the failure, we assign one indicator function I that will tell that when your gx will get 0, you will get 1. Now we will store that failures, right? Total number of failures. Now what your classical definition of probability says, if an event a occurs n times out of n trials, then the probability of getting a is na by n. So what should be the probability of failure here? It's nothing but the total number of failures what we have already collected through the indicator function 1 divided by total number of samples. So this is a very easy concept for this, simulation based reliability analysis. Like if I want to give you a proper visualization of technique, let's quickly go through one simple problem so that you can get the idea. So like,
Quick one. Quick one. How do you generate the random variables?
yeah, that's the big question, that how you will go, how we can generate the random variables, how we can generate the, what should be the number. Yeah, that is the main question. Rest the concept is very clear. We will investigate this thing. Okay, so for now,
Okay.
you got the concept what we are doing in Monte Carlo simulation. Like see this question, see this question. Okay, we have a gx x1 x2 minus 750, and we have generated some sample, random samples. Now says, okay, for
Okay.
this random sample, calculate the probability of failure. So what I said, like, with the generated sample, we need to check how many times my gx is greater than 0, or how many times my gx is less than equals to 0. Now when the gx will be less than equals to 0, I put an indicator function 1 that will give me one value, right? Now check with this pair of generated random variables or random samples. So put it all, replace it in your gx. So first, 37 and 22, 37 and 22, if you put, the value is greater than 1, that means it's a safe. So indicator function will not give you 1. Now second case, it's again 1, that greater than equals to 0, that means you will not get any failure. Now in third case, for 36 and 20, you will get less than 0, that means your indicator function tell you, okay, I have one sample. Now again, if you check for this point, you will have again failure. So total out of these 6 samples, you will have 2 failures. So what will be the probability of failure? It's 2 divided by 6.
Who was? Oh, okay. All right. All right. This is straightforward.
Yeah, that is straightforward. But the question is here, how we can generate the random numbers and how big should be the n to get the proper, proper or desired reliability or probability of failure. If we get the probability of failure, we can
Exactly.
calculate the reliability also. So our task is to generate the random numbers and the n, the numbers, how many, because here in sitting here, how many should be we need to generate, or how many we need to generate to get the result. So this is the biggest question, how we can generate the random numbers. So okay, now here in our MATLAB, now like there are different kind of random number generators we can use, but we have the privilege to use the MATLAB. So here directly using the MATLAB, if you want to generate uncorrelated random variables, so there are inbuilt command. Like you want to generate normal random numbers, this is the command random for normal random variable. We can generate uniform, log normal, Rayleigh, gamma, and all these are inbuilt function are there. But to get this generated random variables, first we need to uncorrelate the random variables, because the MATLAB function will give you the uncorrelated random numbers. Uncorrelated random numbers, like if I give like mu is equals to 30 and standard deviation is equals to 5, and if I generate the random number, it will give the normal random number or normal independent uncorrelated random numbers. Okay, so first what we need to do, uncorrelate things we have already discussed, like we need to perform the eigen operation. And already we have seen the steps. We need to perform an orthogonal analysis where we first need to uncorrelate the correlated space. When we have solved the form and sum problem, we have seen it like x equals to vy, and in uncorrelated space, the mean should be v transpose and ey. What was the v, Bob? This is eigenvalues of Cx matrix. And Cy we will get V transpose C into V, that is the nothing but of lambda. The first step of the form analysis, recall? Yeah. So first what we need to do, if we have a limit state like Gx is equals to x1 x2 minus 1140, what do we need to do? First we need to uncorrelate it. Now, once we have uncorrelate the correlated random variables, now using the MATLAB inbuilt function, we can generate the random numbers. How many random numbers we want? Here n parameter is there. I can get as much I want, I can generate. I can generate. Now I have generated this thing. Now using that generated random number, I can solve the probability of failure. Yeah, Bob, are you want to say anything?
Hello.
Yeah.
Yes, to do the uncorrelation, is that where you convert it from the X to Z space?
No, this is not the Z space. It's just the correlate to uncorrelate form. Recall, in form also, in the first step, we need to uncorrelate our covariance matrix, right? Through an orthogonal transformation.
Yeah.
It's nothing but an eigen operation. Yeah.
Okay.
And the MATLAB
Yeah.
function will give you uncorrelated random numbers. So first, we need to uncorrelate it. We are not going to Z space anyway. It's just the operation of the correlation to uncorrelate. Correlate to uncorrelate space. We have solved it using form, right? The form, first step of form is this. First, that will check our covariance matrix is diagonal or not. If not diagonal, then it will perform the eigenanalysis. Recall the steps of the Haushofer-Linde reliability index and the Rakovic-Fissler algorithm, right? Okay,
Yeah.
so
Okay.
we first need to code it, then we will go here. So the first question is solved. Like, yeah, we can generate different kind of random numbers, or there are different kind of models also, like Box Muller algorithm and all these things. You can check with that. But while you have the MATLAB and it can generate these numbers easily, so go with that. This is very handy. Otherwise, you need to code it and you can generate it using some random seed and random number generator. Okay. So here already we have just like random. It will generate random number of normal variable. Random unif. That means it will generate the uniform random numbers. So we have that privilege to use the MATLAB function, right? Okay. So, so the first question gets solved. We can generate the random numbers of the random variable sitting over the limit state function. Great. Now, so the Monte Carlo simulation concept is very clear. We have Gx, we have generated number of samples, then we check with that generated number of samples. Like we have solved this previous problem using 6 number of samples, but we need 10 to the power 6 minimum, 10 to the power 5 to 10 to the power 6 numbers. So that many times you need to run your code and check how many times your gx is less than equals to 0. That means how many times the failure will occur. So once the failure will occur, it will give you 1, store all the 1, right? Then how you can get the probability of failure? Summation of that indicator, like 1 1 1 1, out of 10 to the power 6, you will get 10 or 15 failures. So that divided by 10 to the power 6 will give you the probability of failure. Clear? It's a very straightforward concept. So first we need to generate random number, then we need to check how many times using that random samples our gx will get 0, and how many times less than 0, and how many times it greater than 0. That means how many times it fail, how many times it passes, right? How many times it fails, we store it, divided by total number of random variables, give me the probability of failure. Now the question is, to get a desired probability of failure, what do we need to do? We need to check with that n. How big should be the n, or what should be the n based on some error and confidence interval. So I hope the concept of this simulation based technique is clear, right, Bob? What we are actually trying to do.
Yeah. Yes. My question is, how do you generate the GX? Can any engineer form his GX, or there's a certain standard where
I
you
am
can
not.
formulate your GX?
I am not generating, or we are not generating GX. We are generating the random numbers of the
No,
random variable of the
I
random.
understand.
Yeah,
I understand. But what I'm saying that now you see the formula GX is given up there.
yeah.
So if I'm doing my design, I want to maybe formulate my GX and use it. I mean, how, how do I go about it to get my GX?
Your
I don't
GX
know
should
whether you get what I'm saying.
no, your GX should be provided in the first step. Otherwise, you will not get the random variables for which
Exactly.
you need to generate.
So there's a
Like we will solve. Let me solve one problem. Then I think your thing will
okay.
get clear.
Okay. All
Just
right.
let me solve one problem. Then you can see. Like you should
Okay.
have to have some GX. Otherwise, you don't have the random variables. If you don't have the random
Exactly.
variables, you don't have. If you don't have the random variables, then how you can generate the random numbers according to them? So GX, you have to have the GX. Limit state, you have to have the limit state, right?
Okay. Okay.
So what was your question?
My question is, for example, I want to do my own design,
Yeah, so you have
and
to have
imagine.
your GX.
Okay.
GX state
So I have
function.
to develop the GS myself.
Yeah, like this one is the GX for the cantilever beam, right? This the limit state function will change for every problem, right? Like for this problem, this one is your GX cantilever problem. For here for the
I
WL,
get it. I get it.
yeah. So you have to
I
have
get it.
your
Let's
GX.
go.
Like you have a casino machine. So that casino machine have some function for the GX, like probability of failure or probability of getting success. So that machine should have some GX for its operation. Now if you have that GX, you can calculate, okay, if you run this much of time, uh, the chances of winning should be this. So you have to have the GX, right? In implicit or explicit form. You know what you are looking for and what random variable actually you are dealing with. That parameter you should have. Otherwise, for what you are doing the reliability analysis. Getting my point?
All right. Okay. Thank you.
Okay. So where were we? The concept that is clear. Now the n. How we can get the n? So basically, here the n, like indicator function, look at the indicator function, it will have two probability, either 1 or I equals to 0. So it's basically follows which distribution? Binomial distribution. Recall binomial distribution have two probabilities, either success or failure. So the n actually we get from the approximating the binomial distribution into normal distribution and calculate the confidence interval. Now here, if we look at the confidence interval formula, this will be the confidence interval, and if we solve for error, we can get the equation related to the number of samples. So if we have some error, if we know some confidence interval, say for example for normal distribution, for 95% confidence interval, what should be the value of k? We already have been went through that. That is 1.96. So for the that k value, and using this equation, we can actually have the number of samples we required to get the desired probability of failure. Like for example, like find the number of samples for Monte Carlo simulation. If look, PF, this is the desired PF. If the PF probability of failure is given, the PF is that error is 10% and for 95% confidence interval. Now look at the formula what we have derived based on approximating the binomial distribution into normal distribution and calculating the confidence interval. So here look at this. This is nothing but your error. Okay, the percentage of error, that error k, that is nothing but the confidence interval, the value of the confidence interval. Like for the 95% confidence interval, the value is 1.96. Now n, this is like if we simplify this, we will get this form. So n, this is the number of samples. P, that is the probability of failure. Probability of failure. So we have all these things like error, epsilon we have. Now we can solve for n. 1 minus p by np to the power half. So we have the error. Error is like 0.1 is equals to k 1.96. Now from where I get the k is equals to 1.96? For 95% confidence interval, the K value is 1.96. It's a standard value. Now, 1, yeah, bomb. 1 minus
Yeah, yeah, it's right. It's right. Yeah.
1 minus probability of failure is 10 to the power minus 3 divided by n into 10 to the power minus 3. And if you solve it, you will get n is equals to this. So, okay. Now, we are in a position, we know how to generate the random numbers if we have gx, and if we know the know the details of the random variables which are sitting over my gx, I can generate hell number of random numbers depending on my efficiency of my computer, or it will take how much time, but it can generate. If I want to generate 10 to the power 10, 10 to the power 11, and 10 to the power 100, it will generate. Okay, so now the question is, what should be the relation between that n number of samples and error? So what I did, I make a plot of the numbers of the simulation. Here this is the in million, that means 10 to the power 5, you multiply it, and this is the percentage of error. Now look, if we want lesser error in our estimation, if we want lesser error in our estimation, what we need more number of simulation, because we are calculating the probability of failure. So to have the probability of failure, we need to have the samples on the failure domain. And we have seen that if we want to have less error in our estimation, we need to have the larger number. Okay, or we can directly go for this equation, and according to our probability of failure and error and the confidence interval, we can easily find it out how many number of samples we need to get the desired probability of failure, right? Okay, so now let's quickly solve one example. Then we will go to the MATLAB, we will code it, and we will check all these results, how we can generate the random number, if the random number will change, if the number of simulation will change, how this will affect our estimation, right? So that is our main task. We need to look into it, and we need to actually investigate these things. So let's solve one example first, then we'll go to the MATLAB and we'll code it, check whether our required number of samples, and compare the results with the form and solve results. That is the main thing. So let's quickly solve one example. Yeah, then we will go to the MATLAB and we will check how exactly this thing will work. Okay, so this problem we have already solved using form, first order reliability method and second order reliability method. So first and second order reliability methods results are already with us. So what was the problem? It's nothing but a cantilever beam of a rectangular cross section subjected to a point load at its free end. Now here we have the variables like P, L and E are the random variables, and they all follows here normal distribution. They all follows normal distribution. Okay, and I is the deterministic quantity, the value of I is already provided. And for the normal variable or normal random variables, we have the mu and sigma value. So for P, if we plot all are the random variables, if we plot the PDF and CDF of these random variables, we will get this. This is the PDF and CDF of P. That means go to the MATLAB, plot PDF using these two inputs. That means these are the normal variables. You have two parameters, mu and sigma. Using these values, if we plot, you will plot the PDF and CDF, you will get the theoretical PDF of these values, right? Likewise, for L and for E, we will get these three curves. You can check it in MATLAB and plot them. So we have solved this problem and we get the result of beta and probability of failure. Probability of failure 10.377 into 10 to the power minus 4 using form, first order reliability method. And in second order reliability method using Brightung approximation, we have the result 9.8122 into 10 to the power 4. Now let's see, if we perform the Monte Carlo simulation, and to achieve these results, how many samples we need to generate, and using these samples, are we getting the results? That is our main task. So let's see, here we have like recall we have this formula to get the n. So let's say we have the desired probability this, because in the first order reliability method we will target it with, say for example, 5.37% error and for 95% confidence interval. Now put all these values in this equation, you will find the number of simulation required to achieve these values. Now see, we need almost 10 to the power 5 number of random samples to get this. So what I did, I generate this many number of samples. Now for each sample I have, you know, checked how many times my GX failed, stored these values, sum them, and divided by the total number, I get the probability of failure. Now in this box you can see our desired number of simulation is 10 to the power 5. So for 10 to the power 5 we can see the Monte Carlo simulation will give almost like 5.66% error with respect to form. And if we look for the sum result, it will very close to the sum result, like 9.81 into 10 to the power 4. 9.81 into 10 to the power 4. So and this is 9.78. So very close with 10 to the power 5 number of simulation. 1 million simulations I required for this. Now it's done. Okay, MCS give me this result. I can say okay, with 5% error I have this result with MCS. Now further to check whether my results are okay or not, what I did, I plot the theoretical PDF and normalized PDF of the random variables as well as the random samples whatever I have generated. So here the blue line, if you can see this blue line, we will plot this. From where we will get this plot, I will see you. So this blue line is the theoretical PDF. Theoretical PDF. Now tell me, Bob, how we can get the theoretical PDF? Based on the parameters of the random variable. So what is that? This is E. E, if I have E follows normal distribution, check for it. E follows normal distribution. This is the mu of E. This is the sigma of E. If I have mu and sigma and I know this E follows normal distribution, can I plot the PDF? Yes. So this is the, actually this is the theoretical PDF. Now here inside this histogram you can see it. This is actually the normalized PDF of the samples I have generated. This 10 to the power 5 samples I have generated for this E. Now I put them in histogram and make the PDF. Now I can see that my theoretical and normalized PDF matched well. That means I can ensure that okay, whatever I have generated the random number, that also follows the uh, theoretical distribution whatever provided in my limit state function. Similarly, for the other two random variables like L and P, similarly I have generated the theoretical and uh, normalized PDF, and see these two PDFs are very close to each other, like the inside one and the outside one are very close. But if I decrease the number of simulation, that will not match. We will see in a minute that if we decrease the number of simulation, that theoretical and the normalized PDF will not match. So the concept is very clear. If we have some results of form and sum, to get that results using Monte Carlo simulation, what we need to do? First, we need to generate the random numbers. How many? We need to, decide based on this equation. This equation we get using approximating the binomial distribution of the indicator function or to normal distribution and calculate the confidence interval, and we get this number. Okay. Now, if we solve another example like this. This is our doubly reinforced beam section. And for concrete failure, the GX is given like this. Here we have three random variable M, U, and FSC. So we have solved using form, and form give me our like PF is equals to 9.2506, and the second order reliability method give these results. Now, if we want to perform the Monte Carlo simulation over it and check whether we are getting the same number of or same probability of failure, so what we need to do first? First, we need to check for the PF. We consider the PF as the first order PF. error, like say for example I have considered 2% error, I want to check it with 2% error. Like you can now you have the idea, like I can further increase or decrease my error, and subsequently with the error and with the confidence interval my number of simulation will increase and decrease and will give me the desired probability of failure or not. Okay, so similarly, first we need to find it out how many samples we need. So here look, we almost need uh, 10 to the power 8, 10 into 10 to the power 8, like 1 into 10 to the power 9 times the samples to convert these results. So here I have performed this analysis using MATLAB. Obviously, you cannot do it using bare hands. So using MATLAB, you can see like 10, for 10 to the power 5, the 8% error, and 10 to the, when we go up to 10 to the power 7, 10 into 10 to the power 7, it's like the error is very close. So I stop the simulation here, and further to check, I plot this theoretical and as well as the normalized PDF. Now, normalized PDF I am getting from the random samples that I have generated to check whether these two PDFs are consistent or not. If they are not consistent, then I need to go for further simulation, or I need to conclude that okay, my estimation in calculation might be wrong at some point of time. So here we can see with 10 to the power 7 samples, we have very close result to the first order and second order reliability method, right? Now again, if we have the correlated case here, for the correlated case I have also generated the random samples and check. Here we can this problem also we have solved using form and solve. This is the very well known problem, 3x1 minus 2x2, we have solved using form and solve. So here we can see the beta form will give this result and sum will give this results. Now if you calculate the n, so I have simulated it using 10 into 10 to the power 6, that means 10 multiplied by 10 to the power 6. So I am getting these results. Now you can see 10 into 8 to the power 7, I am getting very less error, right? So I can say okay, my estimation is okay. I have plotted these two graphs also. For look, for 10 to the power 6 I have plotted these two graphs. Now if you look closely here, the theoretical and the normalized PDF, little mismatch is there, is it right? Now because for if I plot for 10 to the power 7, I will give the proper match of these two PDFs, because for 10 to the power 7 number of simulations I am getting the exact or near to exact values for this simulation. So these are the basic concept. Like further to check, this is the actual row matrix. Like the covariance is given, covariance between x1 and x2, so I can that generate the row matrix. So that will be 1 and 1, and the diagonal term will be, what will be diagonal term? The covariance of this x1 and x2 divided by sigma 1 sigma 2, covariance of x1 x2 divided by sigma 1 sigma 2. Now if you put it, this will be your covariance matrix of the actual that is given. Now whatever sample I have generated, I find out the correlation coefficients, and this is the correlation matrix. And we can see why the 10 to the power 7 will give the closer result, because the correlation metrics are very similar. That means my theoretical and generated random numbers actually matches to each other. So that is all about the Monte Carlo simulation. So quickly revisit that concept, and then we will go to MATLAB and we will plot all these things, how we generate that random number, how we can calculate this, and how we plot these things. We will see one by one. So what we generally do in Monte Carlo simulation, first we have a limit state. We generate the random samples of the random variable sitting over the limit state. Then we assign an indicator function which will count how many times with that generated random samples our GX will fail and how many times our GX will success. So how many times it fail, we store the value. Then probability of failure is calculated based on the total number of failures divided by the total number of simulations. That is okay. Now let's quickly go to the MATLAB and check how we can do the algorithm, how we can, whatever I have said, how we can get the random numbers and all these things. So let's see. First, we will solve this example using MATLAB. So I think the concept, the basic concept, the base is clear, and we see that okay, we need to computationally we need to go or we need to put more effort, but it will give us the results easily. We don't need to transform our limit state into z space. We need to don't need to look for the alphas and betas, then again iterate it, again iterate it. So this is actually basically a handy process. Even I will tell you, if you don't have your limit state in explicit format, in implicit format, if you have your limit state, then also you can imply your Monte Carlo simulations. Okay, so let's see the concepts here using MATLAB. So first, what do we need to do? Like for the first problem,
Hello.
yeah, Bob.
Yeah. Does it mean that before you use the Monte Carlo simulation, you should have done both form and sum before you go on to Monte Carlo
No, no,
simulation?
no, no, no. That not the case, because we here what we are considering the form and sum result, because we have the results and we are checking that for
Okay.
getting these results, how many times we need to, or what should be the number of n, and with that n actually we are getting that or not. Otherwise, like for your case, if someone says this is your limit state, you need to perform your Monte Carlo simulation to get the desired probability
Uh-huh.
of failure, this error is this, confidence interval is this, so you can do it. For this
Okay.
course we took the reference of the form and sum result, because already we have solved this problem and we have seen that these methods are very consistent with each other, because the results are very promising. So that's why, otherwise not
All right.
easy. Okay,
All right. Thank you.
yeah. So first problem, let's quickly solve this problem. Okay, so what was the first problem? We have how many random variables are there in our first problem? We have three random variables, right? One, two, three. So first P, L, and E. So put all these values, mu and sigma of these three random variables we need here. So here, look, I have, added mu. First one, 2500, then 60,000 and 2 into 10 to the 4. And corresponding sigmas of our random variables. Here we can see the random variables. 25 for L, P 60,000, and E 2 into 10 to the 6. So in the sequence you are providing the inputs, you need to look into it, because finally you need to call your limit state function accordingly. So I have given the input. Now index, here I have used for normal distribution, the index is 1 1 1, and the correlation coefficient is not there, so the covariance matrix will be 1 1 1 in diagonal term, no cross term will be there, right? So in Monte Carlo simulation, first what we need to do, using that parameters, first we need to uncorrelate. Like if the correlation, here look, here the row matrix, that means the correlation matrix is diagonally 1 1 1, that means there is no correlation. So first we need to uncorrelate it, right? So what we need to do, we just need to perform an eigen analysis. So first I am calling grn function. Look what that grn function does. This grn function actually uncorrelate your correlated random variables. Look, first what we will check? First it will check your the covariance matrix, whatever you have provided as a input. Is it a diagonal? Diagonal means there is no correlation, right? Now, if not diagonal, it will do the eigenanalysis. After eigenanalysis, it will give the uncorrelated random variables, right? The first step, correlated to uncorrelated. Clear, Bob? First step is done. Now, using that uncorrelated random variables, we need to generate random numbers. Look here. This grn function will give you the random numbers based on the uncorrelated parameters of the random variables. Like if I provide the index is equals to 1, that means it will take case 1, the normal distribution. That means it will generate the normal random numbers using mu, sigma, and n, how many numbers I need. So that should be my input. So how many numbers I need? So to check it, what we need to do, we need to go for this formula and calculate how many numbers we need. Like here I can say we have k value 1.96, error 5.37% for this problem, and probability of failure was this. This was our formula. Like if we go here and check for here, like we have, this is our probability of failure, this is error, and this is confidence interval. I am checking with this data. So with that data, how many number of simulations I require. So if I run this section, I will get the results. Like here. So it says 1.28 into 10 to the power 6. That means almost we need 10 into 10 to the power 5 number of samples, right? So here, look, 10 into 8 to the power 5. I just approximated it with that number. Okay. So basically what we need to provide in our problem, this number in how many numbers I want to generate. So here I have provided the parameter for it in MCS. So 1 into 10 to the power 7. Say for example 1 into 10 to the power 7, that means 10 into 10 to the power 6. So let's see 5. We are starting with 5. That means 10 into 10 to the power 6. That means 10 into 10 to the power 5 number of samples I need to generate. I have provided these values. Now just look at the flow of the algorithm. First, what I am calling that I need, first I am calling the grn function. That means this function, first it will uncorrelate all of your random variables. Then after uncorrelation, it calling grn. That means the random number generator based on index and number of samples. How many number of samples you want to generate. So here I have provided these values, n values and all these values. Now after getting that xg values, that means the samples, I need to count how many times my gx will be 0. So look, now I am calling the gx. That means I need to call the limit state function using that samples, using that sample. So limit state function, here already you have seen the limit state function. Look, for the case 1, this one will be our limit state function, x1 divided by 325 minus x2 x3 whatever it was, that is the limit state function. So I am calling the limit state function from here, and on the next step what I am doing, I am applying one indicator function which will tell me how many times my gx is less than equals to 0, right? So first I have generated random samples. Now using that random sample, I am calling the limit state that many times. That means 10 to the power 5. 10 into 10 to the power 5. That means 10 to the power 6 time I am calling it. Now each every time it is checking how many times my limit state is getting less than equals to 0. Then it count it, sum it. That means count, in count you will get all the failures of the limit state, or how many times your limit state get failed as per these random samples. Then what will you do, count divided by n mcs. That means the number of simulations, like here n mcs value whatever I have provided using that calculation. That through that calculation, like this was the reference point, that many number of samples you need. That's why I am not incorporate that equation directly here. Maybe you should have different kind of benchmark, right? Like you have said, probability of failure can be different, your error can be different. So by this you can change your number of samples, right? So if I run it, what will give me the final mcs values. So let's run it, let's check for the 10 to the power 6 how we are getting the value. So yeah, so plots we will check later. First let's check mcs value 0.001. It's giving the probability of failure 0.001. Now if I want to change the number, look here, I come to the plot little later. So like let's say 10 to the power 7 and again run it. 10 to the power 7 time it is running, so your computer need to be efficient. Okay, so look, in 10 to the power 7 the results have changed. Like we are getting at first we are getting 0.001, and we are getting 9.7 into 10 to the power minus 4, and very close to our results of form. Yeah, very close to our result of form, right? So now we can say that using this number of samples, and this number of sample will decide your error and the probability of failure estimation. Using this 10 to the power 6 samples, I am getting this much of probability of failure. Now, what I use to plot them, like these three plots for three random variables. Look at these three plots for these three random variables. Yeah. So first plot, like plot 1, say figure 1. What I did here, like the theoretical PDF from where I can plot, already I have the values of the normal distribution of L, sigma and mu. So sigma, if I have sigma and mu, just give a comment PDF normal mu and sigma. It will give you the PDF. Now here I have generated the random samples of these three 10 to the 6 time. Now I have stored this result, and also I have plotted the histogram of this. Like figure 1 says O, that means I am taking the results of L, normalize them as a histogram and plot the histogram. That means two kind of cross checks I am doing here. One, I am checking the probability of failure, and also I am, checking the theoretical and that simulated or the normalized PDFs to each other, and we can see the PDFs are actually matching to each other. Like look at, see, blue curve is say the theoretical PDF of E, and the this black one or this normalized one says that this is nothing but the PDFs whatever we have generated using. Actually these are condensed, like look at this thing. Like when I minimize this thing, it will give you the black color, because 10 to the power 6 number of simulations are there. Now if you enlarge it, actually it's red. Okay, because in that portion we actually have that much of samples. I have to shrink it into the histogram and plot this histogram diagram. So now I can say that okay, my theoretical as well as my normalized PDF are okay, and I am getting the result very close to my results of form and so on. Now the thing is, here you can see if I decrease the number of simulation, what happened. Let's see, if I decrease the simulation number of simulation, what happened. So let's say Bob, how many times you want to simulate this? I am simulating is 10 to the power 7. Now tell me a number. Like let's say 10 to the power 1, right? Very simple number. So 10 to the power 1 is very simple. 10 to the power, let's say 10 to the power 4. We are going for 10 to the power 4. Now how much probability of failure? Now look at the PDFs. You are not getting your actual and theoretical PDF are not matching as per your like previous one. This is not. and
Okay, okay, okay,
and
okay.
and very interestingly, let's see the probability of failure what I am getting here. Like look, 0.001, very less value, poor value. Now if I further decrease the number of simulation, like 10 to the power 3, if I go for 10 to the power 3 times, now let's see. Yeah, it's very crude approximation. Look at these two PDFs. Can you call it a
Yes.
you cannot. So the number of simulation is very important to get the, and look at the value of the probability of failure, 1 into 10 to the power minus 3, and it's constant over it. Like like if you conclude that okay, with that number your probability of failure is this and this is your final result, but actually not. You want to re-verify whether your samples are giving the actual densities as per your required densities or not. So the concept is clear how we can do it, and it's very simple. Like you need to have the proper number of samples, and you need to run this time. That means your computer should be more efficient to get these results. Like 10 to the power 6, 10 to the power 8 times, if you are running a limited function and which contains 4 5 random variables, it will take a lot of time, right? That means 10 to the power 6 time it is counting, calculating, and all
Yeah.
the things we are doing. Yeah. Now let's solve another problem. Okay, let's solve another problem. We if we want to solve another problem, like the doubly reinforced beam one. I have added different kind of problems. I will upload these files. You can run it and play with it. Okay. Yeah. So this problem, let's solve this problem. This doubly reinforced beam problem. So we have the limit state here. We have the random variables. We have three random variables, and all are normal. If we don't have normal random variable, don't worry. You just need to change the index, because here I have added, you know, like for normal, for uniform, log normal, type 1, Rayleigh, gamma, whatever distribution you have, just put the index. It will generate. Okay, no issue. Whatever the limit state you have, just define the limit state, number of samples, and this code will do the rest of the thing. I will upload this thing. But my intention is you should understand the logic and flow of these function files, so that in future you can update or change this code as per your requirement, right? For me, it's like to teach them, or to clarify your doubts, or to check the results. I have done these things, but for the research purpose, or for your practical purpose, if you want to perform Monte Carlo simulation over some limit state, or uh, mm, some object which probability of failure you are getting from some limit state, it can be implicit form or explicit form, but if you have the random variables, you can generate it. Okay. So for example, we are going for the this question. So we have three random variable. Yeah. So we will understand the flow and logic simultaneously. So here we have three random variables. So 1, 2, 3. Look here, I am getting mu. So first one, the mu of first random variable, the mean is 100. So here 100 is kilonewton meter. So I've done converted into Newton mm, and 62, and 62, this was in actually. So be careful with the limit units. Convert them as per your convenience, as per your requirement, not convenience actually. Whatever is given, you need to stick with it, right? Otherwise you will get different kind of answers. Now sigma value, look, the sigma values are also given. I'm directly taken it from here, and this content the sigma value, and this is the index. Like all are the normal random variables. So for the random normal variables, I have used the index 1, right? That's why I am giving 1. And this is the row matrix. Now, is there any correlation? No. They are all uncorrelated. If you have any correlation, put it the correlation. First, that GRN file will uncorrelate that, and that give you the results. You don't need to worry about it. Okay. Now, I am calling it, giving that. Okay. First, I am giving 10 to the power 6 number of samples. Now, I have calculated the number of samples for this also, to get this desired probability of failure. That means to check the results with the form and sum. So here we can see we have almost, okay, we have almost 10 to the power 9 number of simulations to have this. Actually, the problem is, if we have lesser probability of failure, we need more and more number of samples to generate. Okay, no worries. Like, say for example, first we will simulate with 10 to the power 6 number of samples. So what the code will do? First, the code will call grn function. Grn function, that means this function file, that will check whether there is any correlation or not. Is If it is not, it will just bypass the uh, uh, that is. Otherwise, it will do the eigen operation and give you the uncorrelated mean and uncorrelated sigma. Once we have the uncorrelated mean and sigma, it is calling the grn function. That means the random number generator function. Whatever I have put here, like I name them like grn, rgn. You can name them as per your convenience. Okay, or you can put all two functions in one function file and make one function file also. No issue. So here, like, after uncorrelating, so here all the things are uncorrelated, so we directly call this function file. So here in this function file, what that grn does, first it will read the index. So index is giving 1. That means it will generate normal random variable using the para means, that means the in para, the mu and sigma is stored. So uncorrelated mu and sigma is stored, so the correlated to uncorrelated space. Or if it is already uncorrelated, so it will get the, or take the uncorrelated values directly, and it will generate this number, this much of random numbers using that mu and sigma I am providing. And n, this is the number of simulations I have already put in my equation, right? Great. Now if I call it now, after that it gave me the number of simulations here, xg. This is nothing but the vector which contain that 10 to the power 6 number of samples of these three random variables. Now, using that samples, I am calling my limit state. So, I need the limit state function. So, here look, this is my limit state function for the W reinforced beam. So, I am calling the limit state function using that variables. That means in that vector, I have already 10 to the 6 number of samples. Now, it will call and check one by one. Put all these values once, check whether my gx function is greater than 0 or less than 0. If it is less than 0, it will count 1. Then again it will check up to 10 to the power 6 number of samples, right? Now after checking it, it will store that uh, value when my gx is less than equals to 0. Now it will count all the values out of 10 to the power 6, how many times my gx get failed, and then the probability of failure using MCS is nothing but all the summation of the failures divided by total number of samples. Now let's run it. We are running it using 10 to the power 6 number of samples. Yeah, using 10 to the power 6 number of samples, we are getting good matches, but let's check with the probability of failure. So we are getting 1.1 into 10 to the power 5. 1.1 into 10 to the power 5. That means 1.1 into 10 to the power 5. Yeah, very close to that. But still, like if we want to increase further, like let's say if we if we increase the number of simulations further, let's see whether our results are getting better or not. Say first I have checked with 10 to the power 6. Now go for 10 to the power 8 directly. Okay, so I think it will take some time, but my uh, this efficiency is good. Yeah, now we can see, like we have, like look, for plotting it is taking time because it need to plot that 10 to the power 8 number of samples in histogram. Till it has not plotted, but it gave me the result. The plot has not done because it need to combine all these values, put it on the histogram and hist command, and then uh, need to draw the uh, PDF. Yeah, it gave me actually this color is not black. If we zoom it, it actually it's red. One sec. Figure 1, figure 2 and figure 3. Any of one I can zoom it. It is not zooming, actually it's still running in the background. So let's finish it till meanwhile we will check the results. Like here with 10 to the power 8 number of samples, we are getting the results very close to the first order reliability method. Look, 9.22 into 10 to the power 6, and we are getting 9.11 into 10 to the power 6, right? So our goal was to check our probability of failure of form and sum using some numerical or the simulation based technique. Here the question and this investigation has resolved. Okay, we have some tool and very popular tool. You have seen that actually works on the classical definition of probability, and it is giving the results, actually the very close results uh, based on the number of simulations. Now is it clear, Bob, how this Monte Carlo simulation things goes?
Yes, it is. As you always say, I just have to sit down and go through, but I think it's getting interesting.
Captain, what, sorry?
I'm saying it's getting interesting.
Yeah, it's yeah, it's interesting actually. For all most of the cases where we don't have the limit state in explicit form, we perform that Monte Carlo simulation millions of millions time. All the casinos, all the poker's games, all the things have their own Monte Carlo models. So Monte Carlo simulation is very popular tool to get the probability of failures based on different kind of numbers, and it is very
Okay,
interesting
so
actually.
so let me ask you this question.
Yeah,
Um, if somebody designs a 20-story building
yeah.
and then you want to be sure that the calculations, everything is all right.
Yeah, everything is all right based on which parameter. First, you need to define which parameter.
Okay, so I'm saying everything is all right because the structure, we know the variables involved in the design and what will make the
Like,
structure very sound.
like that problem.
Materials.
No, that problem can be, we will solve this kind of 12 story frame. I will, if I have time, I will solve. Like for you, I will give some concept. Like, give me some free space. Yeah. So for example, you have a 20-story building. Your case, okay. You have a 20-story building, and you have designed all these things as per your requirement. Now you need to check with the deflection, like deflection serviceability limit state. So g of x will be,
Okay,
say for example, this is your last node, tip node. So g of x will be the displacement of the tip node, say del of this node one, I'm calling it one, minus some
okay,
deflection limit, say l by 325 or whatever it is, as per your
yeah,
case. Yeah, so this is your limit state. So after designing, you need to have the samples of this displacement, top displacement. Now how you can get the top displacement values? Either you can model it using SAP or ANSYS, and from there you can get the value of the top displacement. Now if you have the limit state, you want to analyze this design as per your, or according to your serviceable limit state, or as per your strength, ultimate limit state of strength, you can do it. This is your explicit form of limit state. Here, the random variable del, you can directly call it from the model, whatever you have made in NCs or SAP or ETABS, you can directly get it from there, and you can perform the rest of the analysis and check what will be the probability of failure. This is the one case. Now, if you want to check with respect to serviceable limit state condition, you form a limit state in which story or the entire structure. You just form a limit state for gx is equals to 0. I am calculating some del into minus for the serviceable limit state, some requirement are there in our code. So as per that, you form your limit state, and as per that, you just call this del value and have the Monte Carlo simulation over. Get my point?
all right, all right, very, very clear. Thank you.
Yeah. So that's the thing. What actually you were asking in the very beginning. If we have a design, I need to have a limit state based on which I want to calculate this. Like if I want to, check the reliability against the wind load. So for wind load, I need to generate a G expansion. Okay, wind load will affect this. And my wind code will say this will be the permissible limit. So permissible limits will be your capacity, and this actual model will be your demand. So Gx will be capacity minus demand. You can easily form your limit state from capacity and demand. So the limit state can be easily formed based on the capacity and demand. Capacity is like on which parameter you are looking at. You are looking at the displacement, deflection, stiffnesses, whatever you are looking at, you can check it. Clear? So we will solve some problem. This is actually rich, but you can solve it if you have your model with you. So we can directly link it with MATLAB, and we can generate this number of samples. Like for example, if I want to get the displacement of this node, what I need to do, I need to generate the 100 samples of loads, and I will apply this. And every time am applying this load, I'm storing the results of this displacement. So I have 100 and 1000 samples of displacement. Now check with the your limit state concept. Clear?
All right, all right. Thank you very much.
Yeah. So I think that concept of Monte Carlo simulation is clear, right? So actually, today we will quickly wrap up our session. Actually, I am suffering from some eye infection in my right eye, so problematic. So let's quickly go through another method. Then we will solve these assignments, and we will wrap up our session. So
Okay,
in Monte Carlo simulation, what we have seen, that okay, we can have the desired probabilities, desired failure probabilities, and re-verify it. But what we have seen, that we need much number of samples to converge our result to the accurate one. Now the thing is there any other way so that we can reduce the number of simulation at a time, we will get the better result? The main aim of investigation is that. So adaptive sampling actually does this. Now how I will not adaptive sampling. First, let's go to the importance sampling. Yeah, and importance sampling actually does this thing. Like how? Now in Monte Carlo simulation, let's quickly revisit the things. I just give you the concept. So in Monte Carlo simulation, so this is the problem. This is our limit state. This limit state is formed against limit state of service, limit state of deflection. Now we have simulated 1,000 samples. Now see here, the 1,000 samples are here on the safe region where g of x is greater than 0, and we are not interested the gx greater than 0, rather we are interested where my gx is less than equals to 0. Now here we can see very less number of sample out of 1,000, very less, that means 2 or 3 samples we are having on the other side of the limit state. Now the thing is, if we can specify the region of sampling, if I can tell the algorithm, okay, you just sample here at the MPP, so using less number of samples we can have the desired probability of failure. And the important sampling method precisely do these things, does these things. Like here in important sampling method, we denote the region here like what, MPP, that means most probable points, and the most probable points we can get from the gradient based reliability analysis, the MPP, where we get the convergence. Okay, now if we can define the region, okay, just sample in and around, look here we can have much higher sample on the failure side. That means we required less number of simulations to get the desired probability of failure. Now, we will not go into the theories and all these things. So I think you have got the concept. So probability of failure using importance sampling method. This how this is calculated. Like similarly, we assign the indicator function for gx less than equals to 0 and multiply with some weight function. Here h of x is called the importance sampling density, and generally the importance sampling density is taken as the independent multinormal density. Any other density function can be taken, and we actually define the region using some standard deviation. So we will not go into the theory part, we just go to the algorithm part and we will solve the problem. So first algorithm, what it says, like we need to solve the form problem first, because I need to define the region. So first, normal form problem, we uncorrelate the space, find the extra point in level 2 reliability analysis. Now we need to generate uniform random number generator. Now in this step, look, we are defining the region that using SDM function, that means the standard deviation value, and the SDM value range from 1 to 3, because recall, for the normal distribution, that mu plus minus 3 sigma will cover the 100% of the your almost 99 point something percent of the probabilities. Now the rest of the things are similar to the Monte Carlo simulation. That means we just confine the sampling region. That means we will require less number of samples. So here hx is nothing but the important sampling density function, and that is generally taken as a multinormal density function. This is the multinormal density function. You are very aware of this thing, multinormal density function. Now once we have these two, we can calculate the variance and the error. The error is calculated using the variance, and the probability of failure is nothing but we have the indicator function along with some weight. So weight will define that region of your selection. Now let's see quickly solve one example. This is the flow chart for this important sampling, right? We will start. Now we need to uncorrelate the random variables first. Now find the MPP, then we will do the sampling. Now we will check if how many times my gx less than 0, then we will get the sum. Once we all get the sum, we will go to the probability of failure. It's nothing but the sum divided by ns. So very simple logic for coding this. Now let's check one example, right? So first we have the similar kind of problem. Here we have two random variables. So first we need to perform the first order reliability analysis, and from there we get the extra point where we want to define our region. So extra point I have. Now look, I have defined the region using STM function. Now once I define the region, now the thing is very easy. We need to calculate the fx and hx value. that means the function itself and the importance sampling density we can easily calculate, because we have the random variables and extra points, and once we have this all these values, I can calculate the probability of failure. Similarly, I need to generate that many number of samples and count it, and we can check the probability of failure. So here we can see that number of samples for 200, the probability error is 10, and if we increase the number of samples, this is the result is getting better and better. So with 1000 samples we are getting 4% error, and the probability of failure we are very close to the probability we are getting. So if we increase the number of samples more, if we go to 10,000, we are getting very close to our SOM result. That means when where in Monte Carlo simulation, we need 10 to the power 6, 10 to the power 8 number of samples. In adaptive sampling method, actually, we don't need that much of sample. But to get that liberty, obviously, there should be a trade-off. That means you need to solve the first order reliability method first. You need to define the MPP, and then you need to solve the rest of the problem. So, so first order, if you solve the first order problem, why you go for MCS, right? So this is efficient technique, but you need to give the reason. Now the question is, if I don't want to solve the first order reliability method, can I use the importance sampling method? Yeah, there is a one case that we call the adaptive sampling method. Now in adaptive sampling, what do you do? If we don't have that extra point, if we don't want to solve the form or sum first and get the extra point, so what do we need to do? First, what it does, first it will start with a poor choice, then it will upgrade the choice until we get the convergence. That how the adaptive sampling method works. So I will not go in deep into that adaptive sampling method. uh, that is the research topic. If you want to go into deep, you can try this algorithm, or you can contact me. I will share some additional material to you, but for now I will not go into it deep. So let's solve some example. Okay, so we can see that how and what that simulation based technique does. Now the thing is, choose the correct statement. Okay, adaptive sampling method utilize the fact that even with a poor initial choice of sampling density, the knowledge of the failure domain increase with sampling process. Yeah, actually adaptive sampling does that. If we don't have the extra points, it will start with a poor choice, then it will upgrade the choice of selection. Now the efficiency of importance sampling technique lie on the direction of the region of failure. Yeah, if we don't have, or if we cannot specify the region of the failure, we the efficiency of the importance sampling will not improve. Now this is also correct. Correct. The percentage error in Monte Carlo simulation will decrease with increase of the sample size. Tell me, is it a correct statement or not, Bob?
Correct.
Yeah, it's a correct statement. Very good. And the last one, the percentage error in the Monte Carlo simulation will decrease with decrease of the sample size, and that is the wrong. So correct statements, these three are the correct ones, right? Agree?
Yes.
So this question I have already solved. Instead of, if you have different kind of values, you can solve for PF. Yes or no? Just go through the question and tell me.
I think it's fine.
Yeah, you have the samples. You just need to put all these samples one by one in your GX.
Yeah, yeah.
Check how many times it failed. Put one for them. Here we had 2 times the limit state get failed for these samples. So the PF will be 2 divided by 6. That means 0.33.
23.
0.33. If we have different kind of samples, you just need to replace them in your GX. Check how many times it will fail. Get the probability of failure. Now, second question. Find the number of samples required for the Monte Carlo simulation if the probability of failure is this, and the error rate estimation is 15% for 95% confidence interval. So for 95% confidence interval, we know the K value is 1.96. Here the
Nice.
percentage error is given as 15%. Probability of failure
0.14.
is also given 2.5 into 10 to the power minus 3. And we have the formula that correlates my error with the confidence interval and probability of failure with random samples. And how we get this formula? Approximating the indicator function, that means the
Binomial.
distribution with the thing. Now here we have all the things. Check the value. Is it correct or not? Get me the answer. Check it. I may wrong. Okay, the calculation might be wrong, so please check it. Check it and tell me the value. Are you getting this or not? Just this portion, just check this portion, you will get this. Rest of the thing, I hope it's okay. But still, you need to check once. Like, let me check also. Zero point 9975 divided by 14 into 10 to the power minus 3. So, Bob, are you getting the results?
Yeah, I'm working on it.
0.9975, 9975, 14.6, 687. Yeah, I think this is correct. No.
Yeah,
Okay, so let's move to the next question. So it's very simple. We can solve it. Now we have
yeah.
similar kind. We have similar kind of question here. Error need to be calculated. So find the error in the estimation of failure of probability using Monte Carlo simulation for 95% confidence interval. If the number of samples are given, failure probability is given. So all the things are given. You just need to check. Uh,
Straightforward. Yeah, just straightforward.
It's all provided. Just check with the values, just calculations. Just check the calculations. The calculation might wrong. Okay, so just check with it.
All right. Okay.
Check with it and tell me if you are getting the same results or not. Like if you cross check it, you don't need to cross check it further. You just put in your assignment like this will be the answer.
Four, five.
I think the on-screen calculator will be provided for that. So please practice with that.
Yeah.
No, no, no. In final, those question will be given, which you can easily solve using that. So I already told you on 12th week, we will go through the final questions. How should be the questions? How should be the formula? That day dedicated to the solving the related type of questions. Like we will solve 50 and 60 questions related to like that will, don't worry about it. Just learn it, and I will guide you how the final question will be. Okay, no problem, no issue.
Yeah, it's correct.
Yeah, it's all right, na? So
Yeah, it's
confidence
correct.
interval
Yeah.
is 4.85%. Great. Now,
Yes.
now the third question. Okay. Here actually for two random variables, the CX matrix is given. What will be the B11 term for generating correlated random variables? Okay. If you go through the PPTs, lecture one of this week, so you will get that Box-Muller algorithm and all this algorithm. And after getting the Box-Muller algorithm, we have this. So this formula is already given in your PPT. So I am not going detail. Like if you have the CX matrix, you can directly calculate the B11 value. So B11 value is nothing but sigma 11 divided by under root of sigma 11. So sigma 11 is nothing but your C matrix is given. So 3,
Yeah.
put all these values in 3. So you will get root 3 will be the answer.
Okay.
Now, here, this question is from the impedance sampling method. So here, if the calculated failure probability using the impedance sampling method, yeah, impedance sampling method is already, they have mentioned it here. So PF probability of failure is given. like 7 into 10 to the power 3, and the statistical error. Bob, can you please mute yourself? So PF is given 3%. So what should be the variance in estimation of PF? So what was the relation between the variance and the error estimation in that important sampling? I already have discussed. I think your connection at the time you lost your connection. So I will go to that slide once again. So here, this is the variance to calculate the variance of the important sampling function, and the estimation error E of PF is nothing but your standard deviation divided by PF. Now go to the question and check whether my all values are there or not. Yeah. So probability of error in probability of failure using important sampling method is nothing but your A square means standard deviation of your calculation divided by probability of failure. So the probability of failure already given, the error is already given. You need to calculate the variance. Variance, that means A square. Can you calculate it? Yeah. Already we can calculate it. Already we need to have
Sure.
A square is equals to, it's a simple mathematics, and just put all these values and check.
That's okay. Yeah, yeah, yeah.
Yeah, you have cross checked it, right? Right.
Yeah, that's right. Yeah.
So now move to the next question. Yeah, again it's from the important sampling. So here you need to calculate the hx function. Your gx is given x1 x2 minus 1 1 00. The x star points are given 32 and 31.25. X1 follows the normal distribution with mean 35 and 5. X2 follows normal distribution with mean 29 and 3. Now you need to calculate the hx, that means the important sampling density function, not the value of weight function. Okay, this is inappropriate. This is the value of this call, actually the important sampling density function, right? So okay, no problem, weight function and important sampling density function, we will not get into the conflict. So considering the sample points x1 and x2, extra points we have, sample points we have. Now this hx is nothing but the multi-normal random variable or multi-normal distribution. So we have this multi-normal distribution, like here it says 1 by root over of twice pi to the power n. This is the multiplication sign, 1 by standard deviation expectation of this. Now already we have x and x star points. X, these are the sampling points, these are the design points. So if you simplify this, you will get this equation. Because we have two random variables here, we need to multiply it again for all other random variables. So here we have two random variables, 1 by root pi square, 1 by here sigma xi. So we have two random variables, sigma 1, sigma 2. Now exp minus half x1 minus x1 star square plus, because here also we need to perform the summation because it's a multi-normal random variable. So you need to assemble all the random variable you have in your hand. So now just put all these values. We have the x points like sampling points, we have x star points, all these things. We have sigma values for first random variable, the sigma is 5. For second random variable, the sigma is 3. Now replace all these values and check whether you are getting the result or not. Please do the exercise. So it's very simple. I think you can do by yourself, check by yourself. But just
Yeah, yeah, sure.
check this last two lines. Now, please check this last two lines. So you just need to put the results only. Otherwise, you also need to check further. Do it. No issue. I think we have one more question, or I think this is the last question. No, this is the last question. So just check it.
Mm-mm.
Verify it. Okay.
All right, all right. Thank you very much.
So we are getting the results, right?
Yeah,
So
yeah, it's following.
yeah. So the simulation based technique is like sort of clear. We went through the code of the Monte Carlo simulation. We haven't go through the importance sampling and adaptive sampling. But if you need the codes of this, I will upload the Monte Carlo simulation code along with all the files. So let's quickly go through that files so that you can uh, you can you can update or modify as per your convenience. So basically we have for the Monte Carlo simulation we have three function files. This is the main file from where I am calling the all these things. So I am giving all these parameters, input parameters here, like number of simulations I am providing it manually after getting from the error and probability of failure calculation. Now I am providing the mu and sigma and index. Why index? Because as per that index my grn function file will generate the random numbers. Like if I put index is equals to 1, it will generate the normal random variables as per my mu and sigma, uncorrelated mu and sigma. So first what this code will do, first or using that all values, it will call grn function file. And what that grn function file does, first it will uncorrelate the correlated random variables. That means first it will check my cx matrix, that means row whatever I have provided, that row matrix. Using that row matrix the cx is formed, that cx is nothing but sigma square into row, because the covariance matrix rho is equals to nothing but covariance divided by sigma 1 into sigma 2. So covariance will be rho multiplied by sigma 1 and sigma 2. So first it will check my covariance matrix is diagonal or not. If it is diagonal, that means it is uncorrelated. Don't need to go for any eigen operation. So else, if not, it will do the eigen operation. First it will check my correlation matrix or the covariance matrix whatever I have provided, is it a diagonal. That means is there any correlation term is there. If that, it will do the eigen operation, and after eigen operation it will give me the value of mu and sigma, uncorrelated mu and sigma. Now once we have the uncorrelated mu and sigma, we call rgn function file. That means this, using the index n and uncorrelated mu and sigma. Using the para, I am supplying the parameters of the random variables, whatever I need to simulate using this technique. Now, once this function will give me the number of samples, now come to the code. Here the gx xg, it will store all the random numbers whatever I have provided the input. Based on this input, the xg now content all the generated samples. Now what I need to do, using that generated samples, I need to check my limit state function. So I need to call the limit state function. So for this, here this is the limit state function. This is the limit state function xg1, xg2 and xg3. Look, for three random variable xg all comma 1, that means it will count the first random variable. Xg all comma 2, that means it will collect the second random variable. Then xg all comma 3, it will collect the third random variable, and it will check one by one up to 10 to the power 6 number of or 10 to the power 7 number of simulations. So here it will call the limit state function, replace the simulated value, check. Now after checking, it will check that how many times my gx is less than equals to 0, and that is stored as fe. Now once all these things is down, my count, I am counting how many times my limit state function get failed. So here I can see that count is nothing but the sum. I am getting all these results, and MCS is nothing but that sum of these all failures divided by number of MCS. That means number of simulations whatever I have generated. Like here I have generated this. Now in for the numbers, we have already seen that based on some probability of failure and error, uh, using approximating the binomial distribution into normal distribution, we can have the number of samples to have desired probability and probability of failure and confidence interval. So this is the formula. So this, by this formula we can get the number of simulations. So you can quote this formula too, like here error, like this is the formula. N is equals to nothing but k square multiplied by 1 minus divided by error square. It's a simple thing. So you can run it using MATLAB, and you can then go to there and run all this code and check whether this is not. And the later part, what I have done here. I have, look O, that means xg all comma 1 contain the simulated random variable of x1. So I am, sorting it and plotting it over a histogram. That means all the samples I am arranging over the histogram and getting the normalized PDF of the simulated samples. And simultaneously, hold on, that means it will plot again. What it will plot again? Mu11 and sigma11. That means for the first random variable, mu11 and sigma11, from where you get it? Mu1 for this random variable. And for this random variable, what was the random variable? That was, I think, that was for L. That was for 1000. Like we are solving which question? We are solving question number 1. So question number 1, sorry. Here, question number 1. We are solving the question number 1 here. So 250, 600, and this. So using this mu11, this means actual mu, and sigma of this actual, the given, already given, and I am generating. Now I am comparing these two results. If I run it, so this section will give me the desired results. Like here you can see y is equals to PDF. If you go to this section, it is plotting the histogram of the generated and simulated results like this. So these are actually using the minimum number of samples, and if we increase the actual to the actual number of samples, generated samples, you can have this close match or proper match. Like here I am running it using 10 to the power 3 samples. Now if I increase it to 10 to the power 6 or 10 to the power 7, I am getting the results close to yeah, these are matching to each other, and I'm getting the proper results. You can see the others also, these results are matched and very closely, actually matched very closely. And the probability of failure also we are getting near to 0.001. But further, like if I increase the number of simulations more, then we are getting the results very close to form and song. It is 10 to the power 6, and if I go 10 to the power 7, because for this I hope that I think what I remember that the result was, yeah, uh, 0.99 something, yeah, this. So you can cross check it using any kind of limit state function and the variables. If you have in your hand using this code and Monte Carlo simulation, you can easily find it out what should be the value of the desired probability of failure. Okay. So for now, today, we conclude this at this stage. Okay. So we will meet again on next Sunday. Bob, do you have any doubts or questions? So yeah, you are a structural engineer, right? Can you on your
Yes.
camera? You are
Okay. All right. Hold on.
yeah. So I am also a structural engineer. My background is also a structural engineer.
Yeah.
Yeah.
Good. Are you still recording?
Yeah, I'm recording. Can I stop it?
Yes.
Yeah. So no issue. So let's close our session today here. Then we'll meet again on last next session, and I am closing the recording.